to our lecture on computation heat and fluid flow. Yesterday we looked at the problem of convection diffusion, first in one dimension, and here we have the part from lecture notes that I put on the web and that were written by my colleague Sten Johansen. So we assume that we have the temperature given, so we are solving the 1D energy equation for steady state. Now we want to look at the right boundary. And you see also here something that I ask you to do yourself. Here you have the recipe that the center coefficient can again be expressed as the sum of the neighbor coefficients, AE and AW, minus the coefficient SE from the source term. So that is a good exercise to confirm that. Now we want to look at the right boundary condition. Here we are. So then we continue on this example now, and we consider now to have now the right end of this pipe, where we have now, we focus on the grid point in the cell next to the boundary. So this is now our boundary. So here we have, say we have x, and this is our right boundary, which we denote xb. And we have our western neighbor, capital W, and then we need to compute the fluxes at the eastern face and at the western face. And the assumption is now that we have a convection from left to right. And that means that the temperature at the right is convected. So these are the assumptions. So that we assume that temperature at the right boundary, that is at x equal to xb, is convected. In that cell, that's the case from the cell P. And that means that we then assume that the convective flux that we have here, that is the F, let's see, that is the Ft, that is the convective flux at the right boundary, that is at the eastern face, that can be approximated by Fe, that was rho u, rho is constant, u is given, times the temperature in the cell P. So that is meant that we have a convection then from left to right. So that is one thing, and the other thing, that is the second assumption that we do, that we assume that heat conduction at the eastern face, that is at the boundary, can be neglected. So heat conduction at xb is neglected. And that means then that the QB, that is minus K dt dx at xb is assumed to be 0. So that is an assumption that we make here. If we do that, then we can go into the integral form of the steady one-dimensional heat equation, and that was equation 8. So these are our two assumptions, and now equation 8, that is what I just said, the steady heat equation in one dimension in integral form, that is then approximated in the following way. We have first the flux, the convective flux over the eastern face. There we use what we have assumed here. That is then the Fe times Tp. So the Fe again is given because the velocity is given. And then we have the convective flux over the western phase. And remember, we are still using the central finite volume method. So then we take simply the average of, so first the convective mass flux Fw, rho u is again given. And then we average the Tp and the Tw, or the Tw and the Tp. Doesn't matter in which order we take that. So then we have the convective flux of the western phase. On the right hand side we have the diffusive fluxes, just we have usually, but we have now a special case. That is, now we have this situation here. Remember, what we have to take now, the diffusive flux, is k dt dx. Because the heat flux here is then the integral of minus qb, because our normal is to the right, and in the end we get a plus here, but it doesn't matter, it is 0. So we have no heat flux over the eastern phase, therefore we have here the contribution 0. But we still have a heat flux over the western phase, and that we do in the standard way. And in our notation now we use the diffusive conductance dW that contains then the relevant coefficients, that is a lowercase w, and then we have here Tp minus Tw. And then we have also the contribution from the source term, which was the uniform part plus the part that is dependent on the coefficient times the unknown temperature there. So what we used here is this fact here. That is entering here, that we have assumed no heat conduction over the right boundary, which is now our eastern phase. And we have used that the convective flux is just convected from the cell P to the boundary. So then we have the discrete form, and then we put that in our usual form, that we have everything related to P on the left, everything related to the neighbors on the right. So if we do this ordering, we get the following. We get the d lowercase w minus Fw half. And let's see, from where is that coming? The dW, that is this one here. Minus dW gets a plus, it's this one. Then the Fw half, that is minus Fw, that is this one, that is on the left hand side with Tp, and then we have a contribution from the eastern boundary, that is here. So that gives us then the Fe, and we have a contribution from the source term, which gives us Sp. And that is then times Tp. On the right hand side, we have then something related to W, and that is here, that is with a plus. So that is plus dW, and we will get a contribution from the convection, which is then on the right hand side with T plus Fw half. So Fw half, that is then multiplying T capital W. So, and I think then we have taken that already into account. That is taken into account. The Fe, that we have already considered that. So then only the Su is left. So then we have these, yes?
Why is heat conduction neglected at the right boundary but not the left?
We have the heat equation where we have convection. Something is convected. Then it is naturally that you give a boundary condition, a directly boundary condition on the left, where the temperature is starting. So you know what is coming. So that is somehow a natural boundary condition. On the right, we neglect heat conduction because that is an assumption. And you can think that we cannot maintain the temperature here as we can in a steady case. So we can imagine that the temperature is simply convected over here, and that at the end we have some equilibrium between the interior and the exterior, so that the Tdx is 0. So that is an assumption. That is an assumption. So, but they are physically reasonable. Okay. So then back to this. If we look at this, we can now identify the coefficients, and then we take this here as our equation 17, and the coefficients that we see here are then the AT, and we have here the A capital W coefficient. You see, AE coefficient is not here. So we can, when we want to use it in a general way, we can say, okay, the AE coefficient is simply 0. But now let us look what the coefficient AP is. So the coefficient P, well, first we start with the AW, that is the one that is clear. That is the DW plus the FW half. So they are all lowercase letters. And if you look back what we discussed for the general case, that is just unchanged. There is nothing. If we want to add the AE coefficient, like in the general case, we would simply set it to 0. It doesn't appear in our system. The AP coefficient, however, we have the DW minus FW half plus FE minus SP. And now we use the continuity equation. That was equation 9, continuity equation. This quick continuity equation says that the convective, the convective mass flux, FW and FE, they are the same. That's its continuity. So that means then we have here the DW, and if they are the same, so that means if F little w is equal to FE, because of that, then we get here a plus FW half. And you see that is exactly the same as we had in AW. So then we have taken this and minus SP. So in the end, we see that we can again, so identify that as the AW, and we see that the general formula that we have seen so far again applies, that the center coefficient is the sum of the neighbor coefficients, in our case AW and AE, which is 0, but it doesn't matter, minus SP. So then we have again this form that we are used to. So then we can solve the problem for one-dimensional convection diffusion. And that was with the central finite volume method. Remember, we had a restriction regarding diagonal dominance, that the relation between convection and diffusion, the Cell-Peclet number, had to be smaller or equal than 2. But we get a second order method. So if we have this situation that we have essentially something that is diffusion dominated, not convection dominated, then this is a good method, and we can solve then the system that we get by FVM. Now we want to look at an alternative. And the alternative to central finite volume method is the upward finite volume method. So we have already discussed that in length for the linear advection equation, but there we had the time derivative and the convection term. Now we have just convection, and we have also diffusion. So, but nevertheless, I recommend to look back at the chapter on the linear convection equation, where we had already the discussion for the unsteady problem. Now we look for the steady problem, and we have again the same ideas as before. We look at some cell with a grid point P, with a neighbor E, and a neighbor W. And what we need to compute are our fluxes at the eastern and the western faces of this center cell. So the difference is now how we determine the convective fluxes. So the recipe for the upwind method is determine the convective flux by the value in the upwind cell. So we again do the same thing as we did for the unsteady problem. Put our finger in the air and look from where the wind is blowing, the U is coming, and then we take the value from that cell. So let us see what that means. It means then that we are discussing, remember now, the general case. Before we had the example for the energy equation. The general case is the unknown phi, and we need to compute the phi at the eastern face. And then we look what u at the eastern face, which value it has. If it is 0, then we have no convective flux, because it is u rho u times the unknown. If E is positive, we take the value from P, and if UE is positive, we take the value from P. If U is negative, we take the value from E. That is what this means, and that is what we just write here. So it's phi P if the velocity at the face, which we remember is given, is positive, and it is equal to phi E if the velocity at the face is negative. And similarly, we do it then at the western face to get the phi at the western face. We check the same thing here. We look what is UW. In this case, it's equal UE. And we take then the values accordingly. And that is phi W if the U west is positive, and the phi P if the U west is negative. So then we have here our discretization by the upwind method. And now we remember, we usually don't like that much the if statements. We want to have one formula, if possible, and we remember we can get that formula. And that is, we can express then this in 1 by saying that the Fe that we want to compute, for example, now we look at this here, that can be then, we can write it as Fe times and have this if, or we can do it as we did in, you can look that up that in chapter 4, and in the notes it was the equation 12, when we used another way to express this, and the way we did it was that we take simply the average of this expression that we want to compute, our convective flux, and we do that then for the cell P. So the Fe is given, it's like the U in our linear convection equation, times phi P plus the Fe times the phi E. That would be the central discretization. But then we subtract, in our case it is now we subtract the modulus of Fe times the difference of phi E and phi P. And then we can do the discussion again. If Fe is positive, the absolute value is removed, and then this cancel, and we get 2 times this divided by 2 is Fe phi p. And that is what we get here. And if it's negative, we get then Fe phi e. So that is then the formula where we don't need an if statement. We can write it in a different form so that we see the coefficients on P and E. And that is then the following. That is then 19. Take it first for A. That is for the eastern phase that we are just discussing. That is Fe phi E, or convective flux at the eastern phase, is equal to. And now we simply collect what is going on P. That is these contributions here. So 1/2 Fe, and here minus plus modulus of Fe. So we get the following: 1/2 Fe plus the modulus of Fe times our unknown in P. And let's see, a little bit more space here. So that is then the part related to P. And related to E, we will get this contribution, and from here we get contribution. Here we get plus Fe, and here we get a minus modulus of Fe times phi E. So that is what we get then, plus 1/2 Fe, and here we have now minus the modulus of Fe, the convective mass flux, times phi E. So that is then another way to write the convective flux at the eastern phase. And this term here, the coefficient here, that we call Fe plus. It's defined by this: 1/2 the value plus the modulus. We will discuss that in a minute more. And here, this coefficient here, we call Fe minus. See, it's Fe itself minus the modulus. Before discussing these, let me just write down the situation for the western flux, convective flux. It is just similar, and what we get out of that will be the F western, phi western. They are lowercase letters. That is then 1/2, and here we will then have the upwind is again, that is now we are at west, and we have here the modulus of F west, and that would then be the phi W. And then we have a contribution that will be active if flow is coming from the right. That is Fw minus modulus of Fw times the phi P. Again, we can define these coefficients as plus and minus Fw. And now we want to discuss these coefficients a little bit more. So that is, we can do it in general, so we can just say that what we have here, if we just call it F plus minus, first place we have the definition, it is 1/2 of F, either plus or minus the modulus of F. So that is the definition that we have introduced there. And now we look at the F plus first. The F plus is then f plus the modulus. And what is that? If f is positive, then we can just remove the absolute value. Then we get f plus f, 2f divided by 2 is f. So that we get if f is positive. If f is negative, then the modulus of f, we have still the plus here to consider, the modulus of f is minus f. If f is negative, the modulus is minus f. Then we get 0. So that is the distinction here. And that we can also write as the maximum of f and 0. And that is always greater or equal 0. Right? The f minus is just the opposite. If f is positive, then now we are discussing the minus here. If f is positive, then we can remove the absolute value. We get f minus f is 0. So that is if f is positive. If f is negative, the absolute value of f is minus f. F minus minus gives plus. So we have f if f is smaller than 0. So, and that we can either write as the minimum of f and 0. That is in any case smaller or equal to 0. We could also write it, that's also another way, minus the maximum of, let's say, that is the maximum of 0 and minus f. So that will give the same result. But the important thing to notice that these f plus and minus, they will pick the values of, if f is positive, then the f plus will be equal to the f, and otherwise 0. And if f is negative, the f minus will pick the negative value. And if f is positive, f minus will be 0. So, and that is then reflected here. So if we have f positive, then we will have f here and 0 here. So then we have, this is active here. And the other way around, if f is negative, this will be 0, and this will be f. So in this way, we can express our upwind formula just using these f plus and f minus. So that makes it then the analysis quite simple. So now we use this approximation in the steady one-dimensional convection-diffusion equation. We could see later on the importance of this when we analyze the diagonal dominance of the matrix that we get in the end. So, inserting what I just took away, that is our upwind approximations of the convective fluxes, 19a and b, into equation 8, which is then the integral form of the steady one-dimensional convection-diffusion equation. Then we get the following. The convective flux is now then, as we saw, Fe plus phi p plus Fe minus phi e. That is again, no matter the sign of u. Minus, and here we have now the convective flux at the western side. We do it similarly. Fw plus phi w. And here we have the minus because minus is on the whole flux, and that is the FW minus, and then we have the phi P. So that is the convective flux. The diffusive flux is unchanged. There we have decided to use the central method as we discussed for the diffusion problems before. That is then dE, just the notation diffusive conductance here to make the notation simpler. And here we have phi E minus phi P, convective flux at the eastern phase, minus similar convective flux, the diffusive flux at the eastern phase, and the diffusive flux at the western phase is coming, phi E minus phi W. And the source term we approximate again with a uniform part and a linear part with a coefficient SP. So that is what we get, and then we do the rearranging as we have been doing all the time, getting everything related to P on the left and the rest on the right hand side. So rearranging yields then the following. So that will be then our equation 20. We get a contribution from the dW again here, and from the, let's see, we get here from, let's see, that is underlined, the ones that we have taken into account. So this one is then taken into account, getting with plus when we take it on the left hand side, and this is now taken into account, giving us the FW minus plus, and then the DE that is giving us contribution here. And let's see, we will get also a contribution from here. That will be DE, and then we will get plus FE plus. And we will get the contribution from the source term, that was this one here, minus SP. So that is then phi P. On the right hand side we have the rest. And that is D little w plus F W plus. Let's see, the phi W plus the DE minus the FE minus times the phi E and the uniform part of the source term. So then we have hopefully taken everything into account. Let's see, phi W, that was getting with plus on the right hand side. We have already the dW plus there, right? The dE was already there on the right hand side, and the minus FE minus, that's coming from here. So let's see, yeah, I think we have everything. Now we can identify the coefficients. This is again our coefficient, center coefficient AP, coefficient AW, coefficient AE. So then we can write this also as the following, as 21, that we have AP times phi P is equal to the AW phi W plus AE times phi E plus the uniform part of the source term. So now we can look at the different coefficients and identify them. So in here the coefficients are the following. The A capital W is, we have it there, the dW plus the FW plus. Okay. We can already here note something. The diffusion conductance is always positive if we have diffusion. Otherwise it's zero. So it's always greater or equal than zero. And this here is the coming from the convection, the convective mass flux, and that will be something positive if we have a velocity positive. Otherwise it will be zero. So what we can say that this is in any case larger or equal than zero. So that we can already say here. The AE is equal to, have it over there, the DE minus the FE minus. Here we can also say something, again, diffusion conductance is greater than zero if we have diffusion, otherwise it's zero. This here, the convective mass flux, that is smaller equal zero. With the minus, this is greater equal than zero. So we can also say here, this is always greater equal zero, no matter. So then we look at the AP coefficient now. The AP coefficient is then a little bit more involved. It has the dW, it's all small letters here for these coefficients, diffusion conductance and convective mass flux, minus the FW minus plus the DE plus FE plus minus SP. And now we use the coefficients AW and AE, and we see that the dW here, that is AW minus FW plus. So that means we get here AW minus FW plus, and we had already from the beginning. So that is then the D, let's see, this here is corresponding to the dW minus FW minus, we had that from the beginning. Plus the DE we can express as AE plus FE minus. That is the AE plus FE minus. So this here is corresponding to this here. So this was corresponding to that one. And then we have still the plus FE plus left. And we have the minus SP. Great. Now we have just to remember our definition of F plus and F minus. The definition was that F plus minus was 1/2 F plus or minus the modulus. Now if we want to add F plus and F minus, what do we get? We get 1/2 this plus the same thing with the minus. So this here cancels and we get F. And that we can use now, because we have here F plus and minus with negative, so that means we have here minus FW using this. And here we have FE minus plus, that is FE plus, FE, sorry, FE, just FE. So, then we are in business, because then we see that we have AW, AE, and we have now these FE terms. So we have now derived that AP is equal to AW plus AE minus SP plus Fe minus Fw that we have derived. And now we use equation 9, continuity. This is 0. That is equation 9, continuity equation. So that means we get again what we had all the time before, that we can express the center coefficient as the sum of the neighbor coefficients minus the coefficient from the source term. And we have the nice property that our coefficients now are all greater equal 0, no matter how the direction of the flow is, whether we have diffusion or not. So that is this property. In the end, we get again a tridiagonal linear system that we can solve then with the TDMA, because these properties that we have here will give us diagonal dominance, as long as the source term is the SP is smaller or equal than 0. Let us note this. So again, we get a tridiagonal linear system, as we got for the pure diffusion. Now we get it here also for convection diffusion. And that was 22. A is the matrix, and phi is our vector of unknowns, and SU is then what we have, what the uniform part of the source term. And the A matrix is then made up by our coefficients, where A, I write it here in a symbolic way, that we have the minus AW is the lower diagonal, the AP is the diagonal, and the minus A is the upper subdiagonal. So remember. And the main point here is by that these properties that we have derived here, this matrix is diagonally dominant. Let's see. Well, we can take that after the break.